So actually, I shall speak about a technique which is quite well known, and it's not mine. It's actually was known for quite a long time. But what we did is a kind of modification of this technique, which allowed us to apply it to non-self-adjoint operators and also to discover some new effects. And actually, I shall mostly speak about so I shall first show some simple examples, then I shall show how this technique works for a very simple example. And then I shall just mostly show the models in which it works. And in other more complicated models, I shall only show the main steps without any additional calculations. So I shall begin with a very simple example. So it's a Schrödinger operator on the axis with a small potential multiplied by a small coupling constant. And by epsilon, I always denote a small positive parameter. And all the potentials I shall use will be always smooth and compactly supported. So say that V says from, for instance, C0 on R. And I don't discuss now the sign of this potential. I just say that the graph of V is something like this. So this is X, this is V, and it's something like this. So it's non-zero somewhere in the middle and vanishes outside. Then the question is, what is the spectrum of such operator as epsilon is small? Since the potential is compactly supported, then it can be shown actually it's actually a very simple task to show that the essential spectrum is the following half line with the bottom at 0. And it doesn't matter what is the epsilon and how the potential looks like. We always have that the essential spectrum is this half line. And the main effect says that as soon as we turn on the potential, and as soon as epsilon is non-zero and V is also non-zero, quite often we can have an eigenvalue here. There can be an eigenvalue. And if it's lambda epsilon, then its main feature is that it goes to 0 as epsilon goes to 0. This is true provided, for instance, the potential V of x dx is, it should be negative, yes. So once this is the case, then we always have an eigenvalue. Here it's negative. And the main effect is that once epsilon is 0, we have no eigenvalue. And if epsilon is positive, then we have eigenvalue very close to the bottom of this essential spectrum. So, and actually, I shall mostly speak about such effects, and not actually about the effects, but about the technique which allows to study quite in all details of to study in all details such phenomena. And of course, such model was known for quite a long time, and it's even in Landau's book. It was discussed actually on a physical level. And the first rigorous study, as far as I know, was done by Barry Simon. I don't remember, it was somewhere in 1972 or 3, something like this. Maybe 6 or maybe something like that. I don't remember actually.
But what is the problem exactly?
The problem is, no, it's not a problem, so my lecture will be about the technique which is which should be used for such models, and this is just a simple example.
I mean the following, that you refer to Simon, but some results on this subject are due to Bierman and
Okay, maybe so the earliest paper I saw was this one, maybe.
But what was the result?
The result of Simon was that he proved that there exists an eigenvalue below this spectrum, and he calculated, as far as I remember, its asymptotics, which was like that, with some constant. It was first on the axis, and then it was on the plane, and actually there was also a paper by Simon and Klaus. I don't remember exactly the name, where it was also done in RD for a more complicated operator. Actually, finally it was done for something like something like this. Okay, but this was just an example, and the technique which was used by Simon, so he assumed that V is real and the operator was self-adjoint, and then he referred to Bierman-Schwinger principle, of course. And actually the technique is a variation of this principle. The very basic idea is, of course, based on this principle, of course. So, but I shall first discuss the case when we consider the operator of such form. So, so I shall first write the operator. And I shall write it like this. I shall write it epsilon, L epsilon, where L epsilon will be some operator, not necessarily a potential, but for instance, it can be also a second order differential operator. For instance, an example of this can be the following. Say we have here some a2 d over dx2 plus a1 d over dx plus a0, where all these functions are compactly supported. For instance, we can also think about such operator because it's not necessarily to deal only with the potential, but I don't know actually now. Epsilon is small. Epsilon is small, but what we have here, say it's something like this. We can also think about L epsilon as of an integral operator, say, or this form when it acts, say, something like this. And here we have some kernel, xt, ut, dt. And this kernel is so that, say, we can say that k epsilon says c0, say c is 0, for instance, infinity on R2. Then it also works. So right now, I want to think about L epsilon just as about some operator, and it's not necessarily symmetric. And the question is how to catch this effect, and what can we say about the spectral picture near the bottom of the essential spectrum when epsilon is small, and how it's reflected by the structure of this operator L epsilon. And since now we are in a non-self-adjoint setting, then I would prefer to fix a little bit the notations. So all operators I shall deal with will be closed. So it's a closed operator. Actually, it's even not important to no, what's this? Just think that H epsilon is good enough so that we can speak about its spectrum. And I shall also use the notion of the essential spectrum. And essential spectrum is the set of all complex numbers so that they exist a characteristic sequence or it can be called Weyl sequence. For H epsilon at lambda. It means that there exists a sequence of the functions from the domain of the operator H epsilon such that UN is bounded non-compact and H epsilon minus lambda UN that it tends to 0 as n goes to infinity. Uniform actually.
The norm of UN is bounded from below, isn't it?
And it's non-compact. It can be also said that we can say also that it's something like this. And okay, and actually, what else I need? And also, I shall also need the notion of the point spectrum. It's very simple. The point spectrum is the set of all eigenvalues of H epsilon. So actually, I define the essential spectrum in terms of these sequences. And for the self-adjoint case, this is a way how the essential spectrum is defined. So I just keep this definition for the non-self-adjoint setting, and then I shall speak actually mostly about the eigenvalues. And actually, what we want is to solve the following eigenvalue equations. So we want to find lambda so that for this lambda they exist a non-zero psi so that it solves this equation. And from this picture we know that actually is in a self-adjoint setting this lambda epsilon should be negative. This is why it's quite natural, and this is the first reason, and there are also some other reasons to seek this eigenvalue in such form. So from the beginning, we say that I want to solve such eigenvalue problem. Then actually what we do next is it's a very simple calculations. So we just move this term to the right, and this one goes to the left. This is very simple. And what I do then I just denote. So let's think about this term as about right-hand side. So actually now I want to regard my equation as a usual equation with some right-hand side, and I shall even rewrite it in such form. And then what I want is to solve this equation, and of course I can do it explicitly, because this is a very simple equation and it can be solved, of course. Then the solution of this equation, so I should not make a mistake with the sign. This is the solution. Of course, this is just one of the possible solutions, but I choose it in such form because of the following reason. Assume that k is positive, for instance, for beginning, or more general that the real part of k is positive. And then also assume that f has a compact support. So it's C0 on R, and for instance, that the support of f is inside some segment. Then I know how this function behaves at infinity. So if this is the case, especially if this is the case, then I can say that u of x behaves like 1 over 2 over k. And here I have exponent in the modulus of x. And here will be some constant. And for instance, when this is as x goes to plus minus infinity. And for instance, as x goes to plus infinity, then this constant is the following integral. It's f of t exponent in the power kt dt. So since I have in mind that I have to solve the eigenvalue equation, then of course this function should be from the domain of the operator. And the domain of my operator is actually W22. So at infinity, this function should decay at infinity fast enough so that to ensure the convergence of the integrals in the norms of this space. And since this is the general solution and any other solutions differs from this u of x just by a sum of two exponents, then so actually the general solution to this equation is like this. I can also add this exponent and that exponent. Of course, if I solve this just as a second order differential equation, then of course this is the general solution. But when I say that I want to have a solution in this space, as soon as say k is positive or the real part of k is positive, then of course I should kill these two terms, and then I shall get this formula. So this is the explanation why I choose the solution to that equation in such form, just to ensure that that this function decays exponentially at infinity when the real part of k is positive or when k is positive. This is the idea. And also it's quite important here to have compactly supported right-hand side, and why it is important, it will be clear right now. So I denote this formula, so I shall regard this expression as some operator depending on k acting on f. I can do it, why not? And in terms of this operator, I can solve this equation which I got before in the following form. I can say that when psi is equals to minus epsilon a of k L epsilon of psi. A of k, it's this integral, so I just denote it by a of k. So this is what I do, and yes, and once again, the choice of this a of k in such form ensures that if we find a solution to this equation, then psi will be from W22 as soon as k is positive or the real part is positive. Just because this a of k gives a function which decays exponentially at infinity. This is the choice of this a of k. This is actually how we solve this equation. What's next? Next is that I want to study the structure of this operator A of k in order to be able to solve this equation. We want to find the eigenvalues which are close to the bottom of essential spectrum. It means that our k should be small. So if we seek the eigenvalues in such form, and if we want to catch this effect, it means that k is small. So first of all, I should understand how my operator A of k behaves for small k. And this can be done very easily. So if I say that k is small, what I do is that I just write the expansion for this exponent with respect to k. I just say that it's like this. So this is the definition. And then I just write that this is 1 minus k modulus x minus t plus k squared, etc., etc. And then I just say that the leading term will be just this simple integral. And the rest will be just a1 of k, depending on f. I can write such representation. Of course, since we write the expansion of this exponent with respect to k, and here now we assume that k is small but it's complex valued. It's not important here whether k is real or not here. And this we can do all this thanks to the fact that the function f here is compactly supported. If this is not the case, then of course we don't know whether this is, so if f is not compactly supported, and for instance at the same time where say k is negative, just imagine that k is negative, then this exponent grows as x goes to infinity and t goes to infinity. And then, of course, if f of t is not of compact support, then we even cannot say that this integral is well defined. So it can be also then of course we can also say that f of t decays so that it's c exponent minus some delta of t. But I show just an example. Of course, so from the point of view of this technique, exponentially, so we can have here the exponentially a decaying function f or compactly supported. So this is actually the same. Just for simplicity, assume that f is of course that f has a compact support, and then of course we can do all this. How should we understand this expansion? We should understand it in the following way. So if this is, so let's 1 over 2r f of t dt be a0 of f. Then I can say that a of k can be represented like this. Where a1 is holomorphic in k. Why this is the case is just because a1 acts as follows. It's an integral operator with the following kernel. And if we don't think about the convergence of all these integrals at infinity, then we see that this quotient is holomorphic in K. This is the reason why we can say the same about A1. But now we should specify the spaces in which this A1 acts, and we say that A1 is an operator from L2 on any segment from L2 into W22. So it's a bounded operator from L2 on any segment into W22 on any other segment. And in the same way, we actually regard the operator A of K. So it's also a bounded operator from A1B1 into W22 A2B2. Okay, this is very good. And what we do next is that we substitute this expansion into our equation. What we get? We get the following thing. Actually, there are other ways how to. There are two ways how to work with these equations. Okay, let's do it like this. Actually, no. So we write it once again like that. And instead of writing the equation for psi, I just denote this one by f epsilon. And when I say that psi is epsilon A of K f epsilon, and then what I do is that I substitute this formula for psi once again into this equation. If I do it, then wait, let it be with minus epsilon here, like this. And then it will be like that. And then if I do it, then I get here f epsilon equals to minus L epsilon A of K f epsilon. So there are two ways of writing the equation we shall study later. And the first way is to work with that equation, with that one. Or we can work with this one. And actually, from technical point of view, just due to some technical reasons, this equation actually is in a sense better. Better because we know that f epsilon here has a compact support. So we know that it's supported in this segment. This is the only reason why we work with this equation. But of course, it's also possible to work with that equations. But then actually, the only difference is that we should get the same operator equation, but in another space. And the space for this equation is in a sense simpler. It's better. So what we do then is that we substitute our representation, I mean this one, into this equation. Then we get the following. Minus epsilon, here over K. Here I have L epsilon, A0 of F, minus epsilon, L epsilon, A1 of K, F. And this is, so actually what I do now is actually this Biermann-Schwinger principle. And this is actually what was done in previous work, with the only difference. Actually, I don't, since my operator L epsilon is non-symmetric, and the whole operator is non-self-adjoint, all my operators here are also non-self-adjoint. So I don't care about the self-adjointness property. I don't try to keep myself in the framework of a self-adjoint operators. And in particular, if we again recall this paper by Borisov and also what is done in this Biermann-Schwinger principle, actually the idea was to work only with the self-adjoint operators, and this is why this potential. So while doing this potential was represented by something like this: square root. So the idea was, for instance, in this paper, the idea was to get here also self-adjoint operators, but for the purposes of studying this effect, this is not needed.
Yes, but it is clear.
It is clear, of course.
If you have a small epsilon, then the self-adjoint
is not important. Okay, and this is actually is not important. This is very clear, of course. This is simple, and this is actually one of the way of working with weakly non-self-adjoint operators. So the next step is to rewrite this equation as follows, and to have here minus epsilon L epsilon A0F. And the left-hand side can be rewritten here like that, like this. This is clear. Then we say that since A1 of K is holomorphic in K as an operator acting on this pair of spaces, then this is sufficient to ensure that this operator is bounded uniformly in epsilon. So right now we should assume that L epsilon is also is uniformly bounded. Then we can say that here we have an almost identity mapping, so it's the identity operator plus some small perturbation, and of course it has its inverse, and it is bounded, and it is like this. Epsilon A0F. F epsilon, F epsilon, F epsilon. And we actually solved this equation. This is the solution. Why? Because A0 of F epsilon, by its definition, wait, where is it? It's I had it somewhere here. Wait. So here, A0 of F is not actually an operator. This is a functional. It's a functional working on so A0 maps L2 AB into the set of complex numbers. This is just a constant, and this is why we can move it out. So then we shall get here minus epsilon of K. Here we shall get this constant, and here we shall have just a function of this form, and here will be L epsilon acting on a constant function y, 1. So when I move it out, so what I get here is just 1. So 1 is a function which is constant, and it's 1 on the entire line, and of course L epsilon can act on it. So if L epsilon is a multiplication by a potential, then this is just a potential multiplied by this one. And this is what I get now. Okay, this is very good, because the next step is just to apply the operator the functional A0 to this equation. And then we get here immediately the following thing. A0, and this one is applied to this epsilon A1 of k to the power minus 1, and here epsilon 1, like this. So this is constant, I just cancel it out, and then I move k here, and then finally I get the following equation of such form. So it's f epsilon of k, some function, and this function is exactly this expression. So it's a functional A0 applied to this function. No, it's a function of k. But now, yes, L epsilon applied to 1. And just owing to the properties of A1, since it's holomorphic in K, F epsilon is also holomorphic in K. So what we get here is a scalar equation for K, and actually, in order to find the eigenvalues, we should find the roots of this equation. And once we find such K, the number lambda epsilon being minus K squared is actually the eigenvalue, which was our aim. Moreover, it's also possible to find the associated eigenfunction, because the eigenfunction can be recovered through this identity once we know F epsilon. And F epsilon, since it's an eigenfunction, it is defined up to a constant. We can say that we should choose F epsilon just by formula, just move this constant out, and the rest is known. So this is actually the main idea, the main technique, which is very often used in studying the eigenvalues and resonances emerging from various points in the essential spectrum. And for instance, looking at this formula, it's also very simple to find the asymptotic expansion for this case with respect to epsilon. So namely when epsilon is small, this operator is almost 1. We can write, for instance, a Neumann series for this inverse operator. And then we can say that F epsilon is equals to A0 L epsilon 1 plus something of order epsilon. And if we substitute this formula here, then we get that the leading term is like this.
Can you explain what's the difference with what Simon, for example, does?
The Simon actually worked with the potential. Yeah. This is the first difference. But here we can think about a more general operator. And when Simon did the same thing, he actually so the definition of his operator A of k was different. He had there something like ft, like v in the power 1/2, something like this. The resolvent of this free operator was combined with the square root of the potential. He had something like this. Because in this paper, he says that, there is a sentence something like, following to the Biermann-Schwinger principle, we should work with, so his idea was to stay in the framework of self-adjoint operators. This is why he had to take the square root of the potential of this perturbation, so that he still lives in the area of self-adjointness, and all his operators were self-adjoint. Actually, for his calculations, this was not needed. And this is not also my result, I just now show the result published and made by Gadilshin, and it was published in 2002. Gadilshin. So now I'm speaking about his result. So actually, the advantage was that the O operator can be arbitrary, and we shouldn't think about the self jointness. Actually, yes, exactly. So this is the point, and in order to make all these calculations rigorous, we should say something about L epsilon. And what we say is that L epsilon should be an O operator acting from W22 A of B into L2 A of B. And it should be a bounded O operator from W22 on some interval into L2 on this interval. The norm of this O operator from W22 into L2 should be bounded uniformly. And when we apply L epsilon to some U, which is defined on the axis, it acts actually as follows. So we have some function U. Then we look how then we take its restriction on the segment AB. Then we don't care about the tails, we think only about this part. Then we apply L epsilon to this part. This gives some function on AB. And then we just say that the rest of this function is just 0. This is a localized perturbation, a very simple idea how to define a localized operator. So how to define the localization property. This is one of the ways. So if this is the case, so if we say that L epsilon is just an operator of this form, then all this works, and we have exactly one eigenvalue. And the advantage is also that in this framework we can include all the examples I mentioned. So it can be a second-order differential operator, it can be integral operator, it can be some finite rank operator, actually plenty of them.